Hello and welcome back to another Calculus 3 video. Today we're going to be going over triple integrals. So I guess just getting right into the subject, what exactly is a triple integral? Well, a triple integral is three variable integration. I mean, it's kind of in the name there, wherein, in calculus 1 and 2 we were doing single integration, wherein, we would measure the area under a curve or anything like that. Well, now we're kind of getting into double integrals or multiple integrals, wherein our double integral would calculate the area or the volume under some kind of surface, right? And when we're talking about triple integrals, well, what would a triple integral perhaps be? Well, it'll pretty much represent what the total volume is within a 3D space. So I guess the best way to kind of model this is through my beautiful picture here, where, okay, say we have some function w is equal to f of x, y, z in a domain D. Basically, what I'm trying to say here is that this domain D, well, that's going to be three-dimensional. This kind of function that we have here, well, that's going to be four-dimensional if we really try to graph that. So, unfortunately, I didn't do too much research on how to graph four dimensions. Perhaps we might add like color and sound or something like that at specific points, but I digress. This domain D is really what we're going to be worried about here. So that's kind of modeled in this orangish color. And what are we doing here when we are doing three variable integration? What are we doing? Well, kind of going back to our previous pictures, well, earlier we were summing a bunch of rectangles under a curve or under a surface. Well, think of it this way. A triple integral is doing something very similar. Instead, we're actually going to be making pretty much tiny cubes, right? So these cubes that I have here, they're going to be getting increasingly smaller, infinitely smaller, and that's pretty much what's going to give us the volume or the total something inside of a 3D space. In this case, that is in the domain D. And as I stated prior, we cannot really graph four-dimensional functions. So this w equals f of x, y, z is not going to be graphed. It will be the domain of that will be getting graphed. So kind of getting deeper into what exactly one of those cubes is so that we kind of understand where this integration comes from. Well, one of these cubes is that f of x sub k, y sub k, z sub k. We're making a bunch of little cubes, right? Well, each cube is going to have some kind of width here. Each cube is going to have some kind of depth. And it's going to have some kind of height, right? And when we're multiplying all of these together, well, we're going to get some kind of volume. That is exactly what our volume formula is. It's width times length times height. So that's what we're going to get there. And kind of summing all that together, well, how are we going to do this? Well, our volume is going to be the sum of all of these cubes right here multiplied by that volume, right? That change in volume. And if we take a limit, as each of these cubes gets infinitely smaller, well, that's going to be our integral definition. So our integral definition for some kind of 3D surface and the total stuff inside of it, well, that's going to be the volume is equal to the triple integral of f of x, y, z under the region D. And as you can see here, we have that delta v sub k. Well, that's just going to be dv once we're actually notating it. So I guess kind of why are we doing triple integrals now? Well, couple different applications. Like I just said here, volume, wherein our differential is going to be dv. Our integrand is just going to be 1. We can kind of think of it, well, why would we multiply the integrand by something if we're trying to find the volume, right? So it's kind of intuitive to understand that all we're doing when we're solving for the volume within a triple integral is adding up all of these tiny cubes, right, to get the total size or the total volume within that object. So it's kind of intuitive that we understand why the integrand would just be 1. Mass. So mass is definitely going to be something that we're going to be touching on later on in a couple of videos. But essentially what we're doing is we're multiplying the volume of each of these tiny cubes, and we're assuming that one of these tiny cubes has a density, right? So what does this mean? Well, if we multiply our volume times our density, well, that's going to give us our mass. It's going to give us the total mass of some kind of object. So if one of these cubes has a given density, then guess what? We're going to be able to calculate the mass of some kind of shape. Center of mass, well, that's also something we're going to be talking about further. Similar concept, slightly different. That will be to be determined there. Definitely we'll be talking about that later on. So I guess I'll get back to you on that one. And then finally, another one is kind of probability, right? So unfortunately, as an engineer, I'm not really thinking too much about probability. I'm studying engineering, but what I can say is that if we were given some kind of row that was a probability density, well, if we multiplied that row in the integrand by the probability of that in the differential, then that's how we're going to get a probability density. And there's multiple more. Temperature is definitely one that we'll see in the future, but as for right now, triple integrals have a lot of kind of applications, and it's kind of somewhere where you could argue that the rubber meets the road in Calculus 3. So I guess the kind of how now is, what's the formula here? Well, it's exactly what I had up there. We're going to have the volume is equal to the triple integral of f of x, y, z over the domain D. And this is going to be, instead of a delta vk, that is going to be a dv. And perhaps we kind of understand this by just knowing what exactly a dv is. Well, that's going to be dz dy dx, or dy dx dz, or there's 6 different combinations of what it can be. We'll definitely get into more about what might be the proper way to pick this order. Yeah, that'll definitely be something that we'll get into a little bit further. Kind of similar to how we were talking about that in double integrals, wherein one order may be easier than the other, or one order may be possible compared to another order that is impossible. That's kind of what we're thinking about when we're doing triple integral differential order. So I suppose without further ado, let's just go ahead and get into an example here. So we are asked, I guess, to evaluate the triple integral of 2 minus z dv, where the domain is equal to the set such that xyz is 0 is less than x is less than 3, 0 is less than y is less than 2, and 0 is less than z is less than 1. So we're definitely starting off with a more simple one here. Why do I say it's simple? Well, when we're thinking three-dimensional here, perhaps you're thinking rectangle, but me personally, I'm thinking a bunch of different shapes, some kind of more complex shapes. So this is definitely a good example to just kind of dip your feet in the water here. So I already took the liberty of graphing this already. Well, what are we doing here? Well, essentially, we can see exactly what one of these kind of walls that we made is, what kind of boundary. Well, I just going to start off with a z boundary. Well, we know that z is bounded by 0 and 1, meaning, well, anything between the z is equal to 0 axis and the z is equal to 1 axis, that's going to be free game. And similarly with our 0 is less than x is less than 3, well, what's that saying? That's saying that our x values are bounded by 0 and 3. So I guess that's kind of bounded by this little wall right here, these two. And now finally we get to our y, wherein our 0 is less than y is less than 2. Once again, just saying that our y is bounded by 0 and 2. So that's going to be this kind of wall right here. And when we really make all those shapes together, well, what are we going to get? We're going to get a rectangle here, a kind of box, right? And maybe now we can understand, okay, perhaps if my little cube example up there with the plane wasn't good enough, now we're kind of understanding that, if we sum all of this, well, that's going to be the volume of this. Okay, so let's go ahead and get into this. So we're going to go ahead and make our triple integral now. Gonna have the outer integral, the inner integral, and the inner integral. Sorry, middle integral and inner integral. And we're gonna have our integrand in there, 2 minus z. Now we have to pick our order here. You know, regardless of what I'm looking at here, since this is a rectangle, it's gonna be pretty simple no matter how we do it. So I guess why not just do it in the kind of standard way. The standard way is going to be dz dy dx, right? So let's just go ahead and integrate this in dz dy dx, and perhaps it may be easier that way so that we can just get rid of that dz or the z right here off rip. So okay, let's go ahead and do our method that we were doing when we were doing double integrals, trying to find what bounds were. Well, okay, our z, what's our z? Well, if we just kind of draw some point in the center, draw an arrow all the way up to the very top of this, well, where is it coming in from and where is it coming out from? Well, that is going to be z equals 0 and z equals 1. I'm trying to hammer this in right now because when we're getting to more difficult functions, the bounds may be unclear. And they definitely may be more difficult to find. So kind of going through this procedurally, well, what do we do? Like I just said, pick a point preferably towards the middle, because there's a very high possibility that we might mess it up if we just take it on one of the axes. I guess I need a motivating example for that one. We'll definitely get into one of those later, but pretty obvious here. Well, where are we coming in from? The z is equal to 0 plane to the z is equal to 1 plane, so that's going to be our bounds on our dz. Switching to a different color here, well, what are we doing here with the dy dx? We've already done this before, right? So what did we do when we were doing dy dx? Well, what we were essentially doing was looking at this integral from the 2D graph, right? So if we look down, hypothetically, more metaphorically, I should say, and we squish this box down, what is it going to look like? Well, it's going to look like everything right here. Right, that's basically what it's going to look like, and that could be beneficial to us when we're thinking about how to find bounds later on when we're doing more complex shapes. But our dz, our dy, well, what is our dy going to be? Well, we're going to draw an arrow, or our entrance is going to be from here. We're going to go all the way over here to the very end, draw our little arrow. Well, where are we coming in from? That's going to be our lower bound, and where are we exiting from? That's going to be our upper bound. Well, what is this? That is y is equal to 0, this plane right here, and this is y is equal to 2. So it looks like our bounds are going to be from 0 to 2 for our y differential. Switching to green, let's just go ahead and do the exact same thing for x. Once again, thinking about this as it being squished down into the 2D plane looking above it could be beneficial if we wanted to like draw this shape looking down, kind of like a level curve from the 2D plane, if we really wanted to, for sure. I am just not going to be doing that. For this green one, well, what are we coming in from? We're coming in from this point right here. This is going to be the x is equal to 0 plane. We're exiting right here going this way. This is going to be the x is equal to 3 plane. So those are going to be our bounds for our x differential. So what are we going to do now? Well, we're just going to differentiate how we have been doing. Procedurally, it's no different. We're just adding an extra integral. I guess one other thing that may be different is when we're getting to two more complex shapes, we are going to have more functions within here. Like I said, it's very important that we kind of do sanity checks and say, okay, do I have anything in here now that will stay until the end? So basically what I'm trying to say is if I have a z still when I'm differentiating an x, well, that's going to be a problem, right? In this example, I suppose I should say. So you can definitely do sanity checks when we're doing triple integrals as well, similar to how we were in double integrals. So let's just go ahead and solve this. Well, we're going to have v is equal to I'm going to ditch the color coding here, from 0 to 3 and from 0 to 2 of this integral right here. Well, let's just do this in our head. 2 times z, well, that's just going to be 2z minus 1/2 z squared we're evaluating this one from z is equal to 0 to z is equal to 1 dy dx. Just evaluating this, simplifying it perhaps, we have the integral from 0 to 3 and the integral from 0 to 2. Of 2 times 1, that's going to be 2, minus 1/2 times 1 squared. Well, that's going to be 1/2. So this is going to be 2 minus 1/2. That's going to be 3 halves. And when we plug in 0 over here, well, that's just going to be 0. So this is going to be 3 halves dy dx. Solving this now, we have the integral from 0 to 3. Let's just go ahead and solve this middle integral, or I guess this inner integral now. So our y differential, we're just going to plop a y on the end of that 3 halves. From y is equal to 0, and y is equal to 2 dx. Well, if we plug in 2, that 2 on the bottom is going to cancel. Plug in 0 is going to be 0, so we're just going to have the integral from 0 to 3 of 3 dx. Really simple here. 3x from 0 to 3, which is going to equal 9. That is the final answer, the final solution for this integral. Procedurally, it was an easier one. Maybe unclear to us now why I was doing that kind of box, the arrow method, because, well, why would we need to do that, I guess, is the question. But we'll do a more motivating example here in a little bit. Yeah, without further ado, I guess we can get into the motivating example. Alrighty, so getting into our motivating example for why we might want to use that arrow method that I was talking about earlier. We're asked to find the volume of the region E enclosed by xy plane, y plus z is equal to 1, and y is equal to x squared. Didn't draw this one this time. Let's see if we can draw it together here. Maybe I can talk through it if we don't understand it completely. Okay, well, let's just go ahead and start off one by one. Well, let's color code a little bit here, make our graph pretty. Maybe that'll make it a little bit easier to conceptually understand. Well, what is the xy plane just saying? Enclosed by the xy plane, what is that trying to say? That's pretty much just saying that, well, it stops, our graph stops as soon as it hits the xy plane. So we're not going to be getting below the negative z-axis. Is pretty much what it's saying here. It's saying that all of this down here, the negative z, it's in the dust, right? We don't care about that, so to speak. So we're stopping at z is equal to 0 is essentially what it's saying. Okay, well, if we're stopping at z is equal to 0, well, we don't really need to graph that. We'll just stop when we get to the xy plane. Okay, well, let's go ahead and do the y plus z is equal to 1. That's going to be a plane as well. We're going to draw that. So when we're looking at y plus z is equal to 1, perhaps this is not the easiest to draw yet for us, but we're just going to go ahead and rearrange this. Well, what is this equal to? Well, if we subtract y from both sides, this looks a lot more digestible, I would say. This is going to be z is equal to 1 minus y. Okay, well, we're starting from z is equal to 1, given here. Well, let's go ahead and start up here then. We'll call this z is equal to 1. Okay, ignore how butchered the scale of this is going to be, by the way. We're trying to get the point across, I guess. I'll label my points. 1 minus y, well, this means our y is going to have a negative slope. So that means we're going to start off right here, and we're going to be going downward. And, well, I'll explain that in a second. So I guess we're starting off from the z is equal to 1 and going downward. Okay. That's pretty doable there. Well, what is this doing as well? Well, this is pretty much saying that this plane right here, well, it's going to be getting stretched into infinity, essentially. What that means is that this is not just going to be a line. It's like I said, well, it's going to be a plane. Meaning what? Well, we're going to have... that's not great. There we go. We're going to have kind of like a square looking thing. A plane, it's called. I'm sure we're familiar with this. That's pretty much what our plane is going to roughly, very roughly actually, look like here. So that's pretty much just going to cut through the z is equal to 1 minus y. So meaning, now all we're worried about is this stuff in here, right? Okay, we did that one. Well, what is y is equal to x squared? That's going to be in the xy plane. Okay, we know what y is equal to x squared looks like. That's going to look like a parabola. Looks like it'll stop right there. Well, what is this point right here where it stops? What is that? Well, when our z is equal to 0, well, let's just go ahead and solve for that right here. Well, this is when our z is equal to 0, so that means when we're on the xy plane, z is equal to 0. Let's just plug that into this equation right here. Then we're going to have 0 is equal to 1 minus y. Add that y, so this is going to be y is equal to 1. Okay. And similarly, what is this y is equal to x squared? Well, yeah, in the xy plane it looks like that, right? But in reality, we're going to have some kind of z-naught extending this thing all the way up. All the way up. Right? This is going to be extended up until we hit that y plus z is equal to 1 plane, right? There we go. Perhaps a little bit difficult to visualize right now. Let me just clean it up a little bit. Perhaps I can make it a little easier to comprehend. Perhaps not. Well, basically what this is, I tried so hard on that graph just for it to fail. That's okay. Basically what this is, well, we're going to have a parabola right there. That's going to be extended up through infinity, realistically. And then we're going to have that plane right there. Bang. Cut it off. That's pretty much what this is going to look like. So when we're looking at this from the side, this is the final shape. We'll do this one in whatever this is. This is going to be the final shape. It's pretty much going to be like a... I don't even know what kind of shape this is, to tell you the truth. I'm not even going to sit here and lie. I mean, that's kind of what it looks like, really. I mean, we kind of... Maybe you could visualize that from this, but I think I did a pretty bad job there, and I apologize for that. But regardless, that's what it's going to look like. So this is what our shape is going to look like. Well, let me... I used all my colors. It's okay. We'll make a new color. We'll put this baby in red. Okay. Well, first of all, what do we ask to when we're finding the volume of the region E? Well, basically what this is saying is well, the volume is equal to, obviously, we're going to be using a triple integral over some region E of, what's our integrand going to be? Well, if we recall earlier, when we're doing volume, we're just summing up all of these little cubes that we're going to be making, these this conceptual little cube that we're going to be making. So we're not going to be having an integrand, and that's just going to be our differential. So the volume is just going to be dv. It's going to be the triple integral of dv over the region E. Okay, well, what order do we want to do this in? Okay. I usually like to start off with the dz. So hypothetically, what would happen if we were doing dz? Well, we would be coming from z is equal to 0 all the way up to the top. Once again, this is going to be a motivating example on why we're going to want to start in the middle and use arrows here. Well, we're starting at z is equal to 0. We're exiting at what? Well, this looks like we're going to be exiting at z is equal to 1 minus y, right? That's what this plane is right here. This right here is that little blue plane that we were talking about, right? So, looks like we're going to be exiting from 1 minus y and entering from 0. So, let's just go ahead and write that bound down. Like I said, we're going to be starting in from the z is equal to 0 plane. As we can see from our photo over here, that is the z equals 0 plane. And we're exiting at that z is equal to 1 minus y. So let's just go ahead and extend this. So we're going to have our dz. Now looking at this from kind of like a two-dimensional picture now, like I said, we're going to squish this down to the xy plane. Well, which order would be easiest? Well, okay, we could start off with dx. What would that give us? Well, dx would be the left half of our parabola to the right half of our parabola. Is it doable? Yeah. Does it look like a pain? Yes. So we're going to be integrating from, what would that be? Negative x squared to x squared. I think that'd have to be... not necessarily. That's not. I don't like that. So what's the other order we could do? Well, we could do our dy. What would that be? Well, we would just be starting from this plane right here. Well, anywhere really on this parabola. And we'd be going to this point right here. Well, we already solved for this point right here earlier. This right here, well that is y is equal to 1. So basically what this is it's saying that, well, if we enter from right here and we exit from right here, well, we're going to be entering from y is equal to some parabola that is x squared, and we're exiting out of y is equal to 1. So the bound on that one is just going to be y is equal to x squared and y is equal to 1 dy. So now we know our dx is going to be last. Well, what's our range on our dx's? Well, okay, if we're trying to find the range here, let me use purple actually. Well, what is this value here and like this? Well, we'll use my better photo. What are these two values right here? Well, those values are when y is equal to 1, right? So this right here is y is equal to 1. Well, if we set 1 is equal to x squared, take the square root of both sides, we're going to have positive or negative 1 is equal to x. Meaning this point over here is negative 1, and this point right here is 1. Let's draw our little thing right here. There we go. So, looks like we have a pretty doable integral here now. Definitely more complex than the rectangular integral that we just did. We got some functions in here, but nevertheless, this is definitely doable, especially since we're solving for volume here. So let's just go ahead and move this up here. We're going to have the integral from negative 1 to 1. The integral from y is equal to x squared to y is equal to 1. And the integral from z is equal to 0 to z is equal to 1 minus y. dz, dy, dx. So we're just going to go ahead and evaluate this now. Okay. Evaluating this inner integral first. Well, we're just going to have a dz, meaning when we integrate that, that's going to be z evaluated from our bounds. So we can just rewrite this as negative 1 to 1, and y is equal to x squared to y is equal to, what was that, 1? 1 of z evaluated from z is equal to 0 to z is equal to 1 minus y dy dx. Pretty simple here. That z is equal to 0, that's going to be 0. That z is equal to 1 minus 1. Well, that's going to be what we're integrating in our middle integrand. Negative 1, 1. And then x squared to 1 of 1 minus y dy dx. All right, quick sanity check. Are there any values in here that we're not going to be able to differentiate or integrate in the future. Well, do we have a z? Do we have any other variable other than y and x? Doesn't look like it. So sanity check. Looks like we're doing good so far here. If we had a z in here, then we'd definitely have to go back and look, okay, well, what did I do wrong? Because if we had a z now, then, well, that's not going to be integratable. Well, it will be technically, but we're going to get a z pop out at the output. That's not what we want. We're doing definite integrals. We want values to pop out. Anyway, the integral from -1 to 1, well, let's just go ahead and evaluate this integral right here. dy, well, we're going to have the integrand is going to be y minus 1/2 y squared, going from y is equal to x squared to y is equal to 1 dx. Okay. Well, let's just go ahead and evaluate this one. -1 to 1. Simplify it. Well, we're going to have 1 minus 1/2. And then minus, we're plugging in our x squared now. We're going to have x squared minus 1/2 x squared squared. That's going to be the 4th dx. Can we simplify this? We sure can. Oh, I hope I'm not running out of room. -1 to 1. That's going to be 1/2 minus x squared minus 1/2 x to the 4th dx. So, finally, integrating this one, we're going to have 1/2 x minus 1/3 x cubed minus 1/10 x to the 5th from x is equal to -1 to x is equal to 1 dx. Okay. That's okay. This shouldn't be too bad. We're going to have 1/2 minus, well, all of these are just going to be the same thing, minus 1/3 minus 1/10 minus, oops, -1 right here. Well, this is going to be -1/2 now. This is going to be -1/3, so that's going to turn into positive 1/3. Negative times a negative is a positive. And similarly with that 1/10, this is going to be positive 1/10. Alright, quick sanity check. Are we doing this right? Looks like it. Okay. Well, let me see here. This is going to be negative, sorry. That's going to be 1/2 plus 1/2, -1/3 minus 1/3, and -1/10 minus 1/10. So that's going to be this 1/2 plus 1/2. That's going to be 1. That's done. -1/3 minus 1/3. That's going to be -2/3. That's done. -1/10 minus 1/10. That's going to be -2/10. -2/10 is simplified -1/5. Let's see here. What can we do? I guess common denominator here. What is this? It's going to have to be 15. So we'll do 15 minus 10 minus 3 over 15. That's going to be 5 2/15, I think. 5 minus 10, 5 minus 3. Something doesn't feel right about this. Of course it's the algebra that's tripping me up, right? Once it gets to fractions, that's when everything goes downhill, I guess. -2/10 minus 1/10. That's going to be -1/5. I think I might have done something wrong right here. That's going to be negative. That's going to be positive. No, that's right. It should be. I apologize. I think it's 2/15. Perhaps I did algebra wrong there. If I did, I apologize. Regardless, we set up our integral. We evaluated it. And that is how you are going to do this. Integral right here. Once again, perhaps a motivating example on exactly why drawing those arrows is going to be beneficial, and where we're going to have to solve sometimes for the bounds, right? So we're going to have to solve for when that z is equal to 0 plane and that y plus z is equal to 1 plane intersect. And that's pretty much what we're going to be doing now with triple integrals. Is it won't all the time be like that, but as a general rule of thumb, if we're given something like finding the volume of region E and then we're given region E, well, we're going to have to graph that, and then we're going to have to find our bounds and we're going to have to evaluate it from there. That should be it. Thank you very much.